Hi everyone. Thank you for coming to this session to learn a little bit about automated machine learning. Before I jump too far in, just by show of hands in the back, can everyone hear me okay? Everyone on the internet, can you hear me okay? No, just kidding. Anyway, a little louder. Sure thing, you got it. Just ping me if I need to speak louder again. Okay, so today I am excited to talk to you a little bit about automated machine learning, which is a relatively new research field that I've been very happy to be a part of. So let's go ahead and hop in. Oh, I guess I should say, I'm Randy. I'm the lead data scientist at a little company, startup company called Life Epigenetics. Check it out if you're interested. We'll be hiring soon. So, and we will be working on cool stuff like this. So, okay. Also by a show of hands, I'm just curious, who has heard of automated machine learning or AutoML? Fair number of people, so you're intrigued. Yeah, it's been slowly working its way up through the data science community and research papers and various other things. And I think it's starting to become popular now because we're starting to see some fantastical claims about it, which, being a researcher in the field, that's always fun. We tend to see things like AutoML is a quiet revolution in AI, maybe becoming less so now. Some great posts out there talking about the practical applications of it. So a group out of Airbnb, they made a very nice post about how AutoML is helping improve their machine learning workflows. And then we're even seeing some New York Times articles now, very grandiose, building AI that can build AI, and it's very exciting, but it's also very easy to get lost in the hype of it, right? So today, I want to answer the question, what is automated machine really now, and where is it going? So, to make it concrete, I'm also going to make it clear why you should care about automated machine learning if you're not familiar with it, and how you can use it in your day-to-day data science workflows. So, I really could end this talk right now with one sentence, which the answer to what is AutoML is an approach that aims to automate the process of applying machine learning to data sets. But really, it's much more than that. AutoML is a realization of a growing need in the tech industry, right? So this is a plot I love to put in a lot of my talks. This was a study out of a Philadelphia-based company that basically looked at LinkedIn profiles over time and tried to analyze how many people basically put their role as data scientists over time. And so we see a pretty big growth curve there, right? In fact, between 2010 and 2015, the estimated number of data scientists, self-reported mind you, has roughly doubled. Now I was curious, that was back in 2015, what if we fit a linear regression to it and extrapolate, right? Now, if you're a data scientist, you're starting to cringe because you're like, don't extrapolate outside the bounds of your data. But hey, let's do it for fun anyway. So you're going to cringe extra on the next slide. Okay, so 2015 was where the original data was, and I extrapolated out to 2015, and we see, it's growing quite quickly, right? In 8 years now, instead of 5 years, we've seen 4 times as many self-proclaimed data scientists. Now, I was just for fun, I was like, what if we extrapolate this out, like this growth curve out, until we get the same number of data scientists as there are currently people in the world? And yes, I have to update this slide every time I show these, so that's fun. Thank goodness I have it coded somewhere. But so we see that by the year 3347, we will have just as many data scientists as there are people in the world right now. So pretty impressive, right? But actually, there's a lot more interesting things that'll happen before then, right? I mean, there's supposed to be the first manned mission to Mars around that time. Star Trek Voyager happened around there. Firefly, may it rest in peace, happened around there. Futurama, great show, happened around there. Joking aside, though, the point here is that we all know, the reason why we're at this conference is that we all know data science is a growing field. There's a lot that it can bring both in the business world and elsewhere. And so with automated machine learning, we wanted to build a tool set that these new data scientists especially can use to improve their productivity. So let's jump past the horrible extrapolations now and look at, so if you go and look at any machine learning textbook, most of them will start with some broad statement like this, trying to define machine learning, right? So this is a very popular quote defining machine learning. It says, "A field of study that gives computers the ability to learn without being explicitly programmed." If you've used machine learning recently, or ever, really, you know that that is a load of BS, right? Machine learning still requires a lot of manual programming. So this is sort of a kiddie diagram that I put together to show a typical machine learning workflow, if you will. So of course you're going to start with your raw data. You're going to have to do some data cleaning because data almost never comes in a clean format. A lot of people, some people spend their entire careers there. I try not to. Then, of course, you're going to have to do various forms of feature preprocessing, feature construction, basically reshaping your features or attributes, depending on your preferred vocabulary, into a format that works well for the machine learning algorithm that you're going to apply. Then, of course, you have to choose what machine learning algorithm do I want to use. And then you have to tune the parameters, not only for that machine learning algorithm, but for the entire pre-processing step that came before that as well. And so it's typically there, once you've gone through this whole step, which depending on your level of productivity can take, and the size of the data set, can take a few minutes to a few weeks. Usually that's when we realize, at least our first pass through, that we did it totally wrong, and we have to go all the way back to the beginning. And if we're lucky, we can start back at the data cleaning step and reuse some of what we did there, right? So there is a lot of manual programming that goes into that. We are implementing a lot of things. We're not just putting data into a magic machine and then it spits out predictions for us and makes us a lot of money. So the aim of automated machine learning is to try to alleviate that pain point then, right? We're going to try to automate that entire machine learning workflow, or at least as much of it as we can. So let's talk about the advantages of automated machine learning, and hopefully there's some interesting insights from this section. With some collaborators at UPenn last year, we put together a study. We basically wanted to do a modern version of one of these benchmarking studies where we took 13 algorithms from scikit-learn, which I'm sure a lot of people here use or have used that package. And then we did various experiments with them. We basically tried all the different models, tried a whole bunch of different parameters on 165 different classification data sets. So you can think, some of these data sets came from the UCI machine learning repository, some came from Kaggle. We just pulled together as many classification data sets as we could, both binary and multi-class. And so then we wanted to look at just, basically go back to the groundwork, and retest the basic things that we know are important. So one thing we learned from this, well, really relearned and confirmed, is that default parameters are almost always bad. So what this chart is showing, so on the y-axis, these are the 13 algorithms. On the x-axis, this is showing basically the distribution of predictive accuracy improvement by tuning that algorithm from the default scikit-learn parameters. And basically what we see is that, it varies a little bit, but usually, on average, you can get a 5 to 10% accuracy improvement just by tuning the parameters of your machine learning algorithm, right? Even if you just stick to one, you can get a small amount of improvement that way. Of course, this is part of the aim of automated machine learning, right? Is it's going to do the parameter tuning for you. You don't have to think about that. So AutoML, even modern AutoML nowadays, will solve that problem. Another thing we wanted to look at in this study is whether there is a machine learning algorithm that dominates all the others. If we look at Kaggle competitions, we basically think it's like deep learning and XGBoost, and that's about it. At least last I looked. And so we wanted to go back and say, okay, let's consider these 13 algorithms and basically compete them against each other on these data sets. And so what this heat map here is showing is it's basically, you know, a direct competition, if you will, of the 13 algorithms. So this is putting gradient tree boosting against random forests, for example. And then it's showing the percent out of 165 data sets where the model on the left outperformed the model on the bottom, if you will. And we defined outperformed as a 1% difference, at least, in predictive accuracy, right? And so we see many things that we sort of expect to see. You know, we see that gradient tree boosting dominates, and this wasn't even XGBoost. You know, I have some unpublished work that basically shows XGBoost does even better, of course, but it never beats all of the algorithms, right? Like even in the most extreme case, if we look some of the worst algorithms here, like naive Bayes algorithms, those are pretty crummy on most of the data sets, but there are some data sets where even they will outperform the best algorithms, right? So this is widely referred to as the no free lunch theorem, although one of my collaborators would kick me for calling it that. But basically, it's the gist that we should never assume that one algorithm is always going to be the best algorithm for the problem. And we as humans, we love to latch on to our favorite algorithms and assume that it's always going to be the best, but that's not the case. And I've learned that lesson the hard way in some recent projects. So of course, this is another thing that automated machine learning will help you with, right? It is giving roughly even consideration to many different machine learning algorithms, and so it's not going to be biased towards using any particular algorithm. Now, of course, the biggest consideration for data scientists is the data cleaning aspect. So this is a chart from a recent survey of data scientists, and so this, I'll make it clear, this is not showing the amount of time that people spend on these varying tasks, you know, whether it's cleaning or collecting the data or whatever else. This is the percentage of respondents that said they spend the most time working on these various aspects. And so if we've looked at these surveys in the past, this one was not surprising at all. We know that data scientists spend most of their time collecting and cleaning the data. Now, I'm not saying that automated machine learning will handle all of this for you, because there are just some really nasty aspects of data cleaning that are very difficult to automate. But there are a lot of aspects of data cleaning that we can automate because they follow fairly standard processes. Now, an important takeaway point here that I really want to make is that automated machine learning tools are intended to be a productivity tool. Some places, some people, some companies will claim that it is a replacement for data scientists. You know, oh, you don't need to hire a data science team anymore, just use our tool. And that is patently false right now. I can tell you with high certainty. So just keep that in mind. Automated machine learning, not a replacement for data scientists. It's a data science productivity tool. Okay, I also wanted to talk briefly about the business case for automated machine learning. So this graph is from a recent Kaggle survey. I'm sure some of you have seen it. And the question asks, as a data scientist, what barriers do you face at work? And so I just wanted to highlight some of them here. It's really small on my screen. One very common one that came across is that the company simply can't afford a data science team. Another one was that there was a lack of data science talent for them to actually hire in. And also that the data was too dirty to actually do anything with. They needed more people to work on the data cleaning side, or just a plain limitation of tools. So these are all aspects that are very common problems that businesses face that automated machine learning can at least help alleviate in many cases. So let's talk a little bit, now that we know basically what automated machine learning is and why we do it, let's talk a little bit about the early days of automated machine learning, just to have a little bit of a historical perspective. I promise not to put you to sleep on a long history lesson. It's actually quite a short history. It started around the 90s. And a lot of early automated machine learning focused on only parameter tuning, right? You know, it's like grid search, random search on tuning the parameters of a fixed machine learning algorithm. Some of the more advanced solutions would actually do that search over various machine learning algorithms, and maybe even do a little bit of like fixed data preprocessing ahead of time. We call that model selection. For the most part, they used grid search, where grid search, if you're not familiar, is basically you lay out, you say, okay, these are the parameters, and maybe these are the models I want to consider. You lay out a fixed grid of them, and you just sequentially go through trying them all out, evaluating them according to some metric, and then choosing the best one. Random search has been shown to be a little better than that, where you basically define a range of values for each parameter, and then you just randomly choose those parameters, and that'll work a little bit better. Nowadays, we wouldn't really call this automated machine learning. Some people do. I don't really think that it is. It's pretty basic, model selection and parameter tuning. But of course, times were simpler back then, and we didn't have incredibly large data sets to work with either that we do nowadays. All right. So now let's talk about more modern automated machine learning, which I referred to a little bit at the beginning, right? We want to automate this entire machine learning workflow. And so modern machine learning really came out of the recognition that, one, parameter tuning is important, as we verified with that study. Model selection is important. And then also cleaning and preprocessing the data is also very important to having a successful machine learning application. So we want to include all of these steps in this optimization process. Now, of course, machine learning analyses can be complex. So this is another toy diagram that I put together to just show an example semi-complex machine learning analysis. So it starts on the left here, and we can take an entire copy of the data set, maybe multiply all the features together and create some higher order features there. Or maybe take another copy of the data set, apply PCA to it, combine them together, do some feature selection, fit a random forest on it. So this is basically what we call a machine learning pipeline, right? It can have multiple starting points, but it starts with a copy of the raw data set and sequentially applies operations to them, maybe combines them down the way, and then eventually fits a classifier on it. So this is what we commonly refer to as pipeline optimization. Now, of course, if we're going to be optimizing pipelines like this is a much, much larger space than just choosing an algorithm and just choosing the parameters for that algorithm, right? We have, even if we just consider the 13 algorithms that we looked at from scikit-learn and all their possible parameters, that is a ton of possible pipelines to choose from there. So we're going to need some smarter optimization techniques than just like grid search and random search, although the research community is slowly rediscovering that random search is actually working pretty well at things. But I think that for a lot of these techniques are still worthwhile. So just to give you a very high-level idea of what these optimization techniques are doing, let's go back down to a very simple example in this graph here, where basically we're tuning two parameters for a machine learning model, and we're just trying to find the ideal configuration there. The top plot shows what parameters the optimization algorithm currently thinks are the most promising. These are the ones it thinks it should try next. And then this is sort of the actual distribution based on what it's sampled so far. So as we play this along, you're going to see that whenever a space turns red, it's going to choose that parameter setting, try it out, and then it's going to show up here. And eventually you see that the algorithm narrows in on a particular part of the search space, right? So that's what we want to do with pipeline optimization, except now we're not just doing a 2D search, right? We're doing a potentially 100 or hundreds of dimensional space search, but we're still applying that same kind of idea, right? Where we sample, get a sense of, oh, what's this parameter space look like? Doesn't look promising, ignore it. If it does look promising, keep trying it out. Okay, also as a part of this talk, I wanted to give a sense of what the automated machine learning tools currently look like. So the first one is one that I helped develop at the University of Pennsylvania called Teapot. And so this is more of like a research prototype, publicly available. You can go download it and try it out now. And so the idea here is most of these tools have a programmatic interface. This one in particular is in Python. And if you can see the code okay up there, you'll see it's pretty reminiscent of the scikit-learn interface, right? So actually, let me pause this video before I go on. So we load our data, we may do a train test split, we create our classifier, and then we call fit, right? And then after that, it's automatically going to start searching many different pre-processing methods, many different models, many different ensembles of models and parameters for those as well, right? And so this demo shows, let me skip back again. This demo shows, basically this is sped up, of course. These algorithms tend to be pretty slow, but it shows that on the MNIST data set, you can get about 99% accuracy right out of the box just by feeding the data right in. And then also typically these tools have some sort of export function where you can actually take the best solution at the end of the optimization process and export it back into Python code. In this case, it just generates a scikit-learn pipeline for you. So after, I think a big goal of these open source tools is not to necessarily get you locked into using our tool, right? Like you treat it as an optimization thing, it gives you a solution, and then you can now use that machine learning workflow outside of that tool, right? Okay, and then I also wanted to show a little more advanced, maybe we can call it a commercial solution, which if you stop by the Data Robot booth, you've probably seen this, and I'll just make it clear here. I'm not advocating for Data Robot. They just happen to have a good demo video online, and hopefully they're okay with me using it. I'm sure they are. Okay, so I just wanted to show what it looks like. This is Data Robot is a web-based interface, right? And so of course all machine learning problems start with a question. It's going a little too fast for me. They start with a question. So here we're taking a data set that is actually in an Excel spreadsheet. And the question that we're asking is, given a patient's data at the time of discharge, so this is discharge from a hospital, can we predict if the patient will come back in 30 days, right? Was the treatment that we gave them the correct treatment or a good enough treatment for them to stay healthy rather than having to come back again? And so they'll show in this video the spreadsheet of data, it's highly mixed. Let's pause again. So we have a lot of like yes/no data, which if we're in scikit-learn, we definitely have to convert this to numbers. We have actually text notes here. We have numbers. We even have number ranges for various things. So a highly mixed data set. Right, that if you're a data scientist, you're looking at this like sweating, like, oh man, this is so much data cleaning that I have to do. And even the column that we're predicting here, this readmitted column, is true and false, right? So it's binary classification. So this is a very mixed. It's a fairly structured data set, right? It's in an Excel spreadsheet, but it's not very clean, to be honest. Okay, so then they go into the Data Robot interface, and then you just upload the file, right? You just local file, it ingests the file, automatically processes it, and they're going to, and basically, man, why did I speed this video up? I don't talk that fast. And basically they have a field here where they say, what do you want to predict? What's the column that you're predicting on? So they choose the readmitted column, and then they're also going to scroll down a little bit and show there's various configurations you can do. There it is. There's various configurations you can do. So if you want to do different kinds of cross-validation, or if you want to pre-process any of the variables in a specific way, you can, but you don't have to, right? Basically what they do, they don't mess with it at all, and they just click this giant start button, and it automatically starts running these machine learning analyses on the data. And then you're going to see on the right, they can dedicate a varying level of resources to trying out all of these potential machine learning pipeline solutions in parallel. You're going to see like the memory usage and everything. And eventually it's actually going to show like a leaderboard. You can sort of think of it like a Kaggle leaderboard, just continuously updating as new results come in, which pipelines are performing the best according to some metric that you choose that uses log loss by default. Another aspect here is if you're curious, like I would be if I were using a tool like this, you can actually dig in, what is this pipeline that is performing the best right now? What is it doing? How is it pre-processing my data? What model is it using? What parameters is it using? So on and so forth. So, if you don't necessarily want to use that exact solution, you can learn from it as well. can look up the documentation. And then, of course, you can do a lot of post analyses, right? So depending on the algorithm that you're using, you can get various indications of feature importance, lift charts, all kinds of other things. So post analyses that, if you're familiar with these, you can really dig into, how is this model making its classifications. So I'll go and stop there with that demo. But basically, that's sort of, I think, a great vision for what a commercial automated machine learning tool could be doing, right? There's no programming there, and it has reasonable defaults, and you don't have to be programming on a screen for it to work well. It can find a reasonable solution for you fairly quickly. I believe there's also ways to export those findings. Okay. For the next section, I wanted to, if you're intrigued by automated machine learning now, and you want to give it a try, I want to show you both the free and open source tools that are currently available, or at least some of them. But I also want to show you some of the commercial ones as well, or at least tell you about them, so you can look them up and try them out later. So one of the more commonly used automated machine learning tools out there is called AutoSC Learn. It was basically one of these pipeline optimization tools built on top of scikit-learn. They use Bayesian optimization, and they have a fixed step pipeline. So it's like data preprocessing, where it does imputation, feature preprocessing, and then the model. And it works pretty decently, considering it's an academic research prototype, right? It's available on GitHub, easy to pip install. Might even be on Anaconda. If not, they should get it on there. And that's written in Python, of course. There was, out of the same research group, they also published a tool called Weka, basically the same idea built on top of Weka. So if you like Java, there you go. Of course, there's Teapot that I showed a little video of earlier, also built in Python. Basically the same idea as AutoSC Learn, but using a different optimization technique that is not fixed to that three-step pipeline. I go to research conferences and I rave and rant about how it's important not to have a fixed pipeline that we optimize over. It has to be variable, right? But I don't know. Most people don't care about that. But anyway, if you want a tool that can consider, pipelines that scale up or down depending on the needs of your analysis, check out Teapot. There is, of course, the H2O AI group. They have published an open source AutoML tool. It's called H2O AutoML. And it's written in Java, but they have done a great job porting it with wrappers and various other languages, Python, Scala, R. They have a web GUI. Great to use. It is maybe not as advanced as, let's say, AutoSC Learn. It does some basic data preparation, and then does a mix of grid and random search over various machine learning algorithms. So that's also available online. And then actually there's been a lot of recent research into deep learning. How can we use this automated machine learning idea to tune and automatically configure the deep learning neural network architecture, right? If you have used deep learning before, one of the pain points of it, one of many, is that you have to define an architecture of the neural network from the onset, right? So this deval tool, it's an open source tool that you can use to automate some of that. Expect it to be very slow, right? Like training one neural network on a large data set takes a long time. Imagine training hundreds. So be very patient when you use these tools. One thing I'll especially note here is of these open source tools, the H2O AutoML probably has like the most refined web interface. I wish that I spent more time building a nice web interface for Teapot, but I did not. So if you want a nice jump into a free tool with a nice web interface, a little bit like the data robot one that I showed you, definitely check out H2O AutoML. Of course, we should also look, if you're at a company and your company's willing to spend a little money on this to improve the productivity of their data scientists, we can look into these commercial AutoML tools. I'm introducing this term called Automated Machine Learning as a Service, or AutoMLAS. And if that term has not been coined yet, it's coined now. Got it. Randy Olson, AutoMLAS. That's my contribution. Thank you. Okay, so some commercial AutoML tools. Of course, Data Robot. They're here. You can go and talk to them about it. They have a great web-based interface, great tool. Tons of people to help you jump in and use that. The H2O company that I mentioned, they have built extensions on top of their free and open source AutoML tool, and it's called Driverless AI. From my understanding, it's more or less the same thing, plus some much better feature construction built in there. Of course, there's been a lot of hype around the Google AutoML that's come out recently. This, even though it has a very broad name, at least right now, this is purely just deep neural network architecture search for image data sets. I've heard they're expanding it. I'm really excited to see where they go there. But they have a really great solution for that. And they also have some really great papers out there, like showing that applying these AutoML techniques to deep neural network architecture design, way better than anything we've done by hand. Like more efficient in the sense of more compact neural networks and better predictive accuracy. And then there's a couple others that I've very briefly looked into. You can check out if you're into SAS or SPSS. There's SAS Factory Miner and IBM SPSS Modeler. From my understanding, fairly basic, but built into those tools as well. Okay, so we've talked about what automated machine learning is. We've talked about what it was, and now let's talk about where it's going, at least in my view. So I'm going to break this section up into two major parts, which is one where it's like automated machine learning in the near future, right? Like where I see things I see happening within the next few years, if not the next decade. And then we're also going to have, I'm going to do the stupid thing and predict things that are going to happen way in the future and be completely wrong when we get there. But that's fun anyway. Okay, so let's talk about near future. So automated machine learning we'll be able to handle most of the data cleaning process. Some of the tools now can actually handle that. You saw Data Robot, it was able to handle a lot of the cleaning aspects there. And I also believe that we will be able to automate this transformation of really unstructured data and getting it into a nice tabular format that we can then analyze. One major approach that people are taking right now is to basically look at how human data scientists do it, see if there's commonalities in their approaches, and capture that in the automated machine learning tool, right? Like that's basically the gist of automated machine learning is we want to capture the brains of the smartest data scientists and machine learning engineers out there and put it into a tool so everyone can use it. As I just talked about a few minutes ago, automated machine learning will vastly improve deep learning, as if we thought that wasn't already possible, right? It's this amazing technique, it's solving all the world's problems. Well, now it's going to do it even better through these automated deep neural network architecture design tools that are provided by Google. I'm working on one that hopefully we can release soon, and DVOL and all these other projects that are out there. And then, of course, also, a major part of deep learning is pre-processing the data. You can't just, throw any data set into a deep neural network and magic comes out. You have to pre-process a lot of that data. Automated machine learning can help with that. Another issue that I hinted at with automated machine learning is that they are quite slow, especially on large data sets. Large being hundreds of thousands plus records, or also if you have a lot of features too. You have to be very, very patient for these automated machine learning algorithms to finish their analysis. But I suspect that we will see the runtime of these automated machine learning algorithms speed up tremendously. There's a lot of technologies out there right now, both in terms of parallelizing the analyses, but also just speeding up the individual machine learning analyses as well. And then lastly, in the near future, we will see automated machine learning become human competitive. So, a very exciting aspect of my research has been comparing these automated machine learning algorithms to people's solutions on Kaggle. And what we commonly see across many of the tools is that most of the time, automated machine learning will not get you the #1 spot, but it'll get you in, let's say, the top 5%, or the top 10%. And that's actually pretty good, right? I mean, we're talking about, we just started running an algorithm on a machine, went to bed, woke up in the morning, and boom, it has a good solution for us to some problem that we barely even thought about, right? So that's pretty good. And I suspect that we will continue seeing a trend of that where automated machine learning can get maybe in the top 1% pretty consistently. And we have seen some problems where it's done that as well. And also, just like Google AutoML showed, these automated machine learning tools can be much better at designing deep neural network architectures as well. Okay. Now let's talk a little bit about automated machine learning in the more distant future. Perfect, 10 minutes, good. Yeah, so these are going to be higher level points, a little less practical maybe. So the way I see it, automated machine learning will transform the practice of data science as we know it. One thing that data scientists, especially junior data scientists, are obsessed with right now is like learning all the algorithms, learning all the math of those algorithms, learning all the tools. We get so many questions every day on like what tools, what algorithms should I use, and what we're going to see is that automated machine learning is actually going to relieve us of that, right? So I made it very clear, automated machine learning is meant to be a data science assistant. It's a productivity tool, right? But as these automated machine learning systems grow, as we capture the greater knowledge of data scientists and put it into these automated machine learning algorithms, it can fairly consistently perform at a junior data science or a junior data scientist level, and you give it a fairly clean data set, maybe in a nice tabular format, and it's going to find a nice machine learning workflow for you. So what that means for the practice of data science is that there's going to be less focus on choosing the right machine learning workflow, what algorithm should we use, what parameters, whatever else, and more focus on really the core challenges of data science, right? More focus on posing the right questions. Are we asking the right questions? I've seen some great talks around here that really pivot a common problem that a classification problem that we face, and they say we're not asking the right question here. We have to pivot what question we're asking. But also there needs to be a much larger focus on collecting and curating the right data. As we all know, if garbage goes into any system, you're going to get garbage out most likely. That applies especially in this big data age. And also just generally thinking like a data scientist. Whenever I am looking for a collaborator or someone to work with in general, I really gauge how good is this person at looking at a real world problem and translating it into a data problem. Whatever that means, if the data already exists, great. If we have to collect more data, that is a very important skill for a data scientist, and that is something that we will be able to focus more on rather than worrying about the nitty-gritty details of which machine learning algorithm to use. Another thing I see happening is that automated machine learning will become productized. So this is not like automated machine learning as a service, or AutoML, but more personalized prediction tools, right? So now, if we can get an AutoML system running on someone's phone, we can start, learning and making predictions about their specific data and making personalized predictions. So these are just some maybe silly examples, but just an example of how I think about it is, right now, every night before I go to bed, I say, Siri, set an alarm for 6 a.m., 8 a.m., whatever. Maybe in the future, we can, these phones can learn about our sleeping patterns, when's the best time to wake up, and instead we can just say, Siri, set an alarm for the best time for me to wake up, whenever that is, right? It can automatically learn that, instead of making, assumptions about general population sleeping patterns. It can learn about you and your sleeping patterns. Maybe another example is, Siri, given my personal medical history, if you're comfortable to give that out, should I worry about this rash on my face? Maybe you can take a picture of your face and say, should I worry about this? What does that mean? These are just examples that I could see automated machine learning helping with. There's a big move towards personalized medicine, personalized predictions. Automated machine learning is going to play a big role in that. And then a broader point that I want to make is if you've attended a talk by, say, Jeff Dean, he gives a really great talk about the greater meta-learning movement, right? And automated machine learning, really, I've come to realize, and I think many of us are coming to realize, is just a small part of this greater meta-learning movement, right? And so there's a great quote which I broke down here to explain kind of what that means, right? So computer programming is focused on automating rote tasks, right? If we can define something to be repeatable, we can write a computer program for it to do that consistently over and over again. Machine learning is focused on automating the automation of rote tasks, right? So if we're basically trying to give the computer the ability to learn how to learn these simple, fairly straightforward, repeatable tasks. So then that makes meta-learning the automating the automation of automation. It's very, very meta, right? And basically the idea there is that we're enabling the machine to learn how to best learn, right? Because we program in a lot of assumptions with our training algorithms and our machine learning algorithms that that's the best way to learn, but maybe it's not. Let's let the machine learn how to learn. Okay, we've got 5 minutes for questions. The slides are available at that link. That link, by the way, is 2HS01 capital R lowercase r. It seems typo. Probably someone's going to make a typo there, but yeah, you can download these slides if you want. Hopefully this talk will make it online. Yeah, so if you have any questions or comments or want to learn more about automated machine learning, please feel free to email me or contact me. There's my email address, my Twitter handle, my website. Yeah, thank you for your time. Hope you've learned a lot here, even if you're not interested in automated machine learning anymore. And I'll be happy to take any questions. Question up front. I'll try to repeat your questions, by the way. Oh, awesome. We have a mic.
So the AutoML approach didn't find the top in the Kaggle competition. Was it because it didn't try the same algorithm, or the parameters were different from the top? Oh, did it find the same? So you're asking, did it find the same solutions as the top performing? Yes.
I honestly cannot comment on that in a broad sense, because a lot of people don't share their Kaggle solutions, especially the top performers. So I can't comment on that. I mean, wisely so, right? They want the money. Next question.
Can you give some specific examples of what AutoML can do for data scrubbing, and examples of what it can't really do well now or in the very near future?
Yeah, sure. So some basically data cleaning examples that can be automated now. Imputing missing data, normalizing the data. Basically just think of like all the really basic preprocessing techniques that can be applied en masse in scikit-learn or these other common machine learning libraries. Those are really, really easy to do right now. I think there's a lot of work right now into being able to handle text data better and process that automatically. So on and so forth. In terms of what it can't do, I mean, let's say you want to point an AutoML system at a web page and say, like, predict, something about that web page. If that web page is poorly designed, HTML is all over the place, as far as I know, there's nothing that can do that, right? So if something is really unstructured, it doesn't have even a semi-consistent format, it's going to be really difficult to automate that. And I think that's going to be an ongoing challenge for the automated machine learning research field. Great question. I have a question back there. So I think I saw another question over there too.
Thank you. So the humans who are building models are starting to think about things like bias and discrimination in the models. And with AutoML systems, if it becomes kind of a numbers game where there's a leaderboard now of models, how are we thinking about incorporating some of these things?
Great question, great question. Yeah, so like machine learning is already an issue, right? Because it's a black box that's making predictions, and it's already hard to look into and understand. And automated machine learning, in some senses, only makes that problem worse, right? In the sense of it's a black box that now produces another black box. So, I mean, there unfortunately has not been a lot of focus in the research community on this. I can give you my thoughts on it, which is that if we have a way to quantify bias and discrimination in an algorithm, then we can treat that as a metric to optimize, right? either way, depending on where you want to go with it, right? So I think that's one of the most promising ways to address that issue with automated machine learning. And by the way, that same idea applies generally, to model complexity and various other things as well. If you can find a way to measure something about your machine learning model, you can then optimize that in an AutoML system. Yeah, thank you for that question. Do I have to get off stage for the next speaker? I'm happy. I'm also very happy to.
There's 5 more minutes.
Oh, there's 5 more minutes. Cool. All right. Any more questions? We have some back there. Okay.
So you gave a great rundown of the different tools here. I'm curious from a practical point of view, especially if you're going to use this for something like exploratory data analysis modeling versus retrospective model validation. Do you have any recommendations or best practices given that you'll have finite resources of time to do this?
Yeah, okay, so let me try to recap your question. So basically asking for recommendations on how to use these automated machine learning tools for basically exploratory data analysis, initial modeling efforts in the context of finite resources. Does that sound right?
Yeah, well, are there any best practices you recommend using it for exploratory analysis versus model validation?
Well, I mean, automated machine learning right now, unless you really start going into the better GUI-based ones, it probably isn't going to be super helpful for exploratory data analysis, right? It's not going to generate those reports for you and plots of distributions and various other things. So AutoML is more used for once you have a decent understanding of the data and you think that you would be ready to start applying machine learning algorithms, even just to get a sense of like how useful is this data for predicting this outcome. I would say it's useful then, right? Like what I commonly do, even with Teapot and these other tools, is before I jump in and start going down my common practice of okay, let's throw a random forest at it and see how it works. I just on the side fire up an EC2 node and just have it go, start running these AutoML tools on the data set just to see what comes out, right? And a lot of these tools design it in a way that even if you have limited resources, you can interrupt them and say, just give me what you have now after 12 hours or whatever else. So I think that's a good practice for using these tools is to just consider it, something on the side that can hopefully probably help you find a better solution to your problem. I think we had a question back there first. I think we can jump back there. Okay, so let me try to recap your question. This is a fun challenge. I'm an automated translation tool up here. Okay, so I think your question is, are there any tools to help understand these models, especially as these models get more and more complex, as presumably they will be when they come out of these automated machine learning tools? That is an active field of research again. There are some existing tools. I use like Lime fairly heavily, and there's a new tool out there. I'm forgetting the name. On the spot, darn it. There's a new tool out there that I obviously haven't used much yet. But basically these tools are able to take any black box classifier and then analyze them in a way that you can get, usually local explanations of what that model is doing. So that's sort of the best I've seen so far. And one thing that I really try to focus on in AutoML is thinking about optimizing machine learning analyses as a trade-off between like classification accuracy or predictive ability and complexity, right? We should be thinking about that, not just throwing a crazy deep neural network at it and saying, yeah, okay, that works. Let's try to get the simplest possible analysis that can perform well, and then even look at a trade-off, like if we go to the simpler analysis, how much predictive ability are we sacrificing there? Got a question over here. I hope I'm not missing anyone.
This will be the last question.
Last question, okay, and then we can talk outside.
So, first, thanks for the talk. And were you referring to SHAP, by Scott, that framework?
SHAP, yeah, exactly. Yes,
so
SHAP, S-H-A-P.
And that was for the question. And second, about Teapot, I was a bit curious. What do you use for hyperparameter optimization? Do you use like Bayesian optimization or like tree Bayesian estimators like HaperOpt, or what do you?
Yeah, so we use, and this is purely personal bias, I use this technique called genetic programming, evolutionary computation. It would take way too much time to explain that to people who don't know what it is, but it's just another optimization technique. If you want to look it up, I recommend it. It's a super cool technique, although it's a little bit frowned upon in the machine learning community, but maybe one day. All right, thank you everyone. I'll be happy to talk outside.
Let's get Randy a warm applause.